Data science has been becoming a growing profession and is also the heart of many organizations. That's why Data Science Portugal was born. The first community created by data scientists for data scientists. DSPT wants to gather anyone who works in the field and chat about any topic over this great subject. All members from our team are committed to make sure that the data science field evolves in a healthier and stronger way. To ensure that the focus is on sharing knowledge, we guarantee that our stage is not a place that supports any commercial or recruitment content, and our kind speakers are committed to share their experience for free. We want you. Let's do bigger things together. Join us at any event all around Portugal or online.
And we are live with the 80th meetup of DSPT. This DSPT meetup will be in webinar format due to the coronavirus situation. But nonetheless, we have an exciting talk, which is Deep Multimodal and Cross-modal Embeddings, which will be by David Smith. I'm Lucas Fischer. I'm a member of DSPT, and I'm joined with here is Mario, a familiar face for those of you who have been tuning in on these webinars. So, Mario, if you want to say a few words.
Hello.
Yeah, a few words is just one word, but sure, let's go. The title of this meetup is Deep Multimodal and Cross-modal Embeddings, as I said. So it's basically trying to work together with different modalities that exist in real life. So, for example, audio and text, and how we can combine them so we can extract better patterns together. So I'll just give a quick overview of how the webinar is going to look like today. So I'll just go through a quick introduction. Then I'll move the stage to David Smith so he can talk to us about his talk. And then we'll have 15 minutes of Q&A where you can submit your questions here on the YouTube comment section. And we'll make sure that they are given to the speaker, and they all appear here on your screen. And then we'll close out this webinar. So the introductory video, if you had the chance to view it, basically explained what DSPT is and what it stands for. But I also want to quick underline some other topics. So we are present in these 5 cities of Portugal. We have local teams there, and we do in-person meetups. So if you ever want to join in on an in-person meetup when this quarantine or this coronavirus situation normalizes a bit, it's in these cities you can do so. And you'd want to follow our website at datascienceportugal.com. It's a good centralized way of having all the information about DSPT, as well as generic information about the data science community here in Portugal. So we have past events of DSPT, also upcoming events. We have some other information like jobs related to data science and courses related to data science. So it's a good resource for you to have. We're also present in various different social medias. So if you want to talk to us, or if you want to talk to the community, this is where you can do. So we are present in Slack, Facebook, Meetup, and LinkedIn. And these are the number of members in each of these social medias. So if you have a topic, if you have a question you'd like to talk to the community about, feel free to join in. You don't have to be a data scientist or anything. You just have to love this field as like we do. And feel free to join in, and we'd love to have you to discuss your topics. So I just want to go quickly to a quick word of thank you to Bosch for supporting this meeting, this webinar. So thanks, Bosch. And I want to ask you guys for proposals of talks. So if you've been working on something interesting these quarantine times, or if you know someone who's been doing an interesting project or an article or a blog post or whatever, and he wants to share with the community, please feel free to join in on and fill in the information on our call for proposals. And we'd love to give you a stage and have you present your ideas or your colleagues' ideas to the community. You have here the link, and the slides will also be available on GitHub, so you can find the link there as well. So speaking of next events, we have an upcoming event this next week, actually. So it will be on August the 6th at 6:30 p.m., if I'm not mistaken. It will be the 81st meetup of the DSPT, but this will be a partner event with DevOps Sports Community. So it will be a webinar with 2 talks, and make sure to remember the date and be there on August 6th. We also like to promote different partner events of the DSPT. So the upcoming event that we have is on September 7th and September 8th, which will be the summer school on machine learning and big data with quantum computing techniques. This will be by the University of Porto. So speaking of the talk that we have today, this will be presented by David Semedo, which is a researcher at the Web and Media Search Group at Nova. He recently finished his PhD, so this month, if I'm not mistaken, at Nova University of Lisbon. So he successfully defended his thesis. So congratulations, David, on this. His thesis was about multimodal machine learning, which is also his interest. And he's been working on this field since 2015. So he has a lot of experience that he'll share with us today. So without further ado, we'll be presenting deep multimodal and cross-modal embeddings by David Semedo.
So, hello everyone. First of all, thank Lucas for your very kind introduction. And also thank you for the invite and for the opportunity to present this webinar. So, today I'll be talking about deep multimodal and cross-modal embeddings. And before I start with the actual webinar, let me just give you some information about myself. So, like Lucas said, I'm a researcher at the Web and Media Search Group from Nova, which is a research center in the Nova University of Lisbon. I did a PhD, so I just concluded it 2 weeks ago in deep learning for multi-bit understanding. And my topic was about bringing the time dimension to these neural cross-modal embeddings. I will be talking about this in a moment. And well, my main interests are around multimodal machine learning, at combining these computer vision and natural language tools to have multimedia understanding systems that combine these two things together and really can do clever things. So, to start with the talk, let me just give you a brief outline of what I will be talking about. So, I will start with just a motivation of why do these things matter, and then I will give you the basic building blocks and some of the different approaches that you can use to learn these kind of models. And I will show you some of the state of the art and also some of applications, some scenarios where you can apply this kind of embeddings. And then I will conclude with some final remarks. So the first thing is that if you think about it, the world is actually multimodal. So it's very hard to come up with a scenario where you only have one modality or you only have one type of information. Usually you have two or more. So, for example, I have this example here, which is something quite remarkable. So this was published last year. And this basically is a model that can answer questions and also provide a rationale for those questions, for the answers that it provides to the answer. So if you look at the image, you can see that there's this woman pointing a gun to another person, and there's a guy in the background trying to rob the bank, possibly waiting for some key lock combination or something. Well, if you look at the answers that the model gave to the question, why is person one, so the woman pointed to person two, you can see that it actually made a very good prediction, and the justification is just, it's also correct. Basically, it's because there's a guy in the background and, well, they are robbing a bank. So both the answer and the justification are correct. The main point here is that even though this is quite awesome, because, well, it's a very good result, this was completely automatic. And the important thing to realize is that in the background, there's this model that can really combine vision and language and all the elements that you can see in both the questions and the answers, and also the visual part in a very efficient manner, and be able to do this, which is quite good. There are other scenarios. For example, in the medical domain, you have this work that they consider different types of diagnostics, so different modalities again. So each modality in this case was a specific medical exam, where they use this to do tumor segmentation. So they want to help doctors and segmenting or pointing the regions of the image where there may be a tumor. So they found that they can really increase the performance when they consider multiple modalities. And there are other examples. Another one is navigation. Well, you can think of robots, self-driving cars, well, everything that involves navigation or autonomous navigation, where you have one of the modalities are the vision part, which can be RGB or infrared cameras. Then you can have sensors, proximity, depth, etc., etc. And there may also be speech. For example, someone would like to give an instruction to a robot and he has to process it and act accordingly, etc. So these are just examples of situations, real scenarios where you really, in order to succeed, you really need to combine multiple modalities. And this is the goal of these multimodal embeddings, to help addressing these tasks. To give you just a brief overview of and some definitions. And so basically a multimodal just stands for several modes when you are looking at individual modalities. So different views for the same sample, but you can think of it as just different representations, okay, for different views of your information. And then a multimodal embedding, which is the target of this talk, is basically a vector representation where in this embedding, so in this embedding space, you will have information that combines information from your multiple modalities. So the first question we need to ask ourselves is, why would we want to model or to combine multiple modalities, right? And I have this example which I think clearly shows the importance of these kind of things, which is you have this image and you have its description. And if you look at the image and if you didn't add the text, it would be very hard to guess that this was the Deep Time light show at the Edinburgh Festival. Although you can think on the other way around, if you only add the text without the image, it would be very hard for you to guess what the Deep Time light show would look like. So if you combine the two things, you can actually get a better view of everything that involves your sample, in this case, this image and this text. And this is the reason why we are interested in this. So once we realize this, there's this important notion between structured and unstructured information. So in structured information, one example is tabular data. After you vectorizing this data, you can pick a specific column, for example, age, and you can discriminate between each row, each sample, just by according to their age, right? So you have structure in your data representation. In images, in text, in audio, and time series, and this kind of information, a single pixel, which would be the equivalent of a single column, it's not, but just to make the example clear and simple, in an image, a single pixel does not tell you anything about the image itself. So you need to look at the image as a whole or several parts of the image. And the same applies to the other modalities. And these, the models that I will be talking about today are all about tackling the problem of modeling this unstructured information and combining multiple modalities of unstructured data. So the first thing is that you do, well, you have two modalities. The first thing you can do is that let's extract some features to represent them. So I have text here, and I have text in the first, as a first modality. As a second, I have an image, and I can extract some vector representation. Just choose any feature vector that you want, feature representation that you want. The important thing to realize is that these representations are heterogeneous, so they are not compatible. Okay? They are completely different. And you could just do something really simple, which is one type of early fusion, which is concatenated to vectors, right? And then use it as you want. Well, this has some issues, because if the representations are not well aligned, which is the case that I'm showing here, well, you are combining two things that are very different. This may not work well. Another thing is that you are assuming that if you give this vector, this concatenated vector to another model, you are assuming that this single model can take the most out of each individual modality. And usually the models that work better for text and for image have some similarities, but they are not quite exactly the same. And finally, well, since we are using directly these initial feature representations, you are limiting the capability to unveil complex correlations between the two things. Right, complex correlations in the sense that how the two things interact, the image and the text. And this applies to other modalities as well. So one step which you can do is, and this is the first multimodal embedding approach that I will show you, is learning a joint representation, but instead of just concatenating everything. So you have this kind of network where you have 3 inputs. It would correspond to 3 modalities. You can have as many as you like. And for each modality, you do a set of nonlinear transformations, which are the layers. You can add as much as you want. And then you combine everything on this final representation. And what this vector will give you is a combined representation of your 3 modalities. And this is a type of late fusion. And well, this is quite good because we have a multimodal representation already, but there's a catch here. We are assuming that at training time and at inference time after training, we have these 3 modalities always. If you don't have one of these modalities at inference time, for example, you cannot use this model. Okay, that's why a different approach of achieving these multimodal embeddings are the coordinated representations or the cross-modal embeddings. And the idea is very similar, but instead of having a network that somehow is connected, all modalities are connected at some point, you keep everything separate. So like you can see here, you have one branch for one modality, another branch for another modality. And what happens here is that you force the output of these 2 networks to be aligned. So if we are talking about the distance metric space, this would mean that they should be in the exact same point. And with this, after training, if you don't have one of the modalities, you can still use just the branch from the modality that you have, and you can project your data to a multimodal embedding space and keep doing your thing. So these are the 2 main approaches, okay? And now let's dive into each of these approaches by starting with a linear cross-modal embedding. So before jumping in nonlinear approaches, or more complex ones, the simplest thing you can do is just learning a projection matrix. So here I have the same paired information, an image and its description. This X represents the image and the Y the text. And what you want is a matrix that projects this vector to space, and the same for the image. And this vector space is actually combining the 2 modalities. So it's a common subspace. So what this means is that these 2 vectors now, they should be in the exact same point because, well, we know that they are correlated. They are in the same pair. So this is approached with canonical correlation analysis. It's a very old tool, but it works fairly well. It's available on scikit-learn. It's very easy to implement it and to just use it from scratch. And basically, here you maximize correlation. So the idea is that you know that these 2 things are correlated. So you just want to learn a projection, a linear one, that maximizes correlation on this embedding space. And this is the simplest model which you can come up. But like I said, it's a linear model. So the important thing to understand here is that we can ask ourselves, do we know a priori how any 2 of these modalities are correlated? For images and text, we can have some ints, right? But it would be very hard to mathematically express those ints, right? And one way that people started approaching this kind of problem is by using neural networks, because as we all know, they apply a set of nonlinear projection functions that we can learn these projections according to our loss function and our task that we want to approach. And well, from the universal approximation theorem, we just need enough neurons or hidden layers to approximate any function. So people started using these neural networks as the backbone for these models, which kind of makes sense. So the first approach which you can think about is just a kind of an autoencoder. It's trained as an autoencoder, so you give it an input representation and you force the network to reconstruct that representation. But you can see here there are 2 input modalities, and in the middle of the network you have a common representation. So the output of this layer here actually encodes information from the 2 modalities. So what this means is that we have a multimodal embedding. So what can you do with it? So first of all, this architecture is very easy to extend to other modalities. So you can add more modalities, and you can perform multimodal queries with the output of this vector here. And then you can also use these features on a classifier on another task. that needs to combine information from these two types of information. Well, it's good, but it's not a cross-modal embedding yet, because, like I said, you are still stuck with the need of having the two modalities at inference time. So the second approach, which I show you here, it's another building block, and is basically keeping the same idea of training an autoencoder, but now you have two separate branches, right? So you have one for the text and one for the images. And basically you have a shared code layer, and this code layer basically is the same layer. It's basically you share the weights. So it's a way of sharing information between the two branches, but you keep them separate. They are completely independent. So like I said, it's still an autoencoder, but now the difference is that they are independent. So this is a true cross-modal embedding. Well, after this, a lot of people started doing research over this and improve these kind of approaches. A second model here, which I'll present to you, it's based on the canonical correlation analysis, the one that I've shown you before, but it basically adds these neural networks before to allow the model to do some kind of to do some nonlinear transformations before it actually computes the canonical correlation analysis loss function. And what it allows, what it does is allows the model to unveil these complex correlations that I was talking about before computing the final projection function. And this model is still quite effective nowadays, even though it's unsupervised, so it does not use any class information, but it works quite well, and I will show you the results in a moment. So, like I said, all of these models that I presented you are unsupervised. They already use neural networks to get these nonlinear projection functions, but we can actually do much better than this, because if we use class information, so take again a look at this example where we have this image, two images and descriptions. So the image at the right, it has the word deep time light show, okay, but the one at the left does not. And it would be very hard without supervised information, without class information, to propagate this information to the image at the left. But since you know that they share the same class, they are both representing the same semantic concept, basically you can give this to your models and the model can propagate the deep time light show to this image. And then you can get a really rich embedding space. So one way to achieve this is basically train the networks that I've shown you before, but using a classifier as a proxy. So here I have one branch for the images, one branch for the text, so it's the same as we've seen before, but then you have a final layer which is in which its dimension is the number of categories that so basically it's the number of categories that your data set has. And then if you have a multi-class setting, you can use categorical cross-entropy, or otherwise if it's multi-label, you use binary cross-entropy. Well, I'm sure that you all know a lot about this, but basically the main point is that you train the model to learn a classifier, but as you propagate the error, you are actually tuning these final representations here, so you are learning implicitly the cross-modal embedding space that we want. And this is one way to do it. The second way is with metric learning. So to give you an idea of metric learning, so the idea is that instead of learning a classifier, we actually will come up with a loss function that directly reflects the structure that we want. And the structure in this case is that, well, we want these two things to be in the exact same point, so we just use a loss that enforces this directly, instead of using a classifier as a proxy. So to give you an idea of one kind of ranking loss, which you can use, so there's triplet loss. It's very widely known and it works fairly well. So the idea is very simple. You start with an anchor element, so it can be an image, a text, or whatever, and then you find a positive, and notice that here we are using class information, so the positive is some element that has the same category, or the same class, and then you find a negative one, something that is completely unrelated. And then you enforce the similarity between the anchor and the positive to be greater than the similarity between the anchor and the negative plus a given margin. So to help you visualize this, so this would be our space. It's incorrect because the anchor is closer to the negative example than to the positive. This is not as we want. So we enforce this constraint, and after learning, we fix it, and basically we end up achieving the structure that we want. And then you just keep enforcing this constraint over several of these triplets, and you end up achieving a good structure of your embedding. So to give you some more details on how this is approached, so you can convert this constraint into this form. So basically it's a differential function now, so we can optimize it. And like I said, you sample several of these triplets, okay? Randomly, you can choose any strategy that you want. And basically, for each of these triplets, you enforce one of these loss terms. So, and then you sum them, you can also average them, and then basically you combine the loss, and then you train our model using this information. And well, this is one way to do metric learning, and it works quite well. We recently proposed a different formulation for the triplet loss. So if you look at this constraint here, we have a constant value here, and we proved that if we change this value by a function, you can increase the expressiveness of this equation. And if you tie this to the optimization part, so you can really get much better performance. And to show you this, I have these results here. So this is the results on 3 data sets. Usually what we do to evaluate these kind of models is we start with an image as a query and we find texts. So basically we navigate the embedding by finding texts, and then we do the opposite thing, text to image. And well, and then we report the average of the two. And this gives you a good overview of the state in terms of performance of all the models that I've presented to you. So CCA is the linear approach. So, well, its performance is quite low. It's normal, it's a linear approach. But once you start looking at the nonlinear one, so all of these here, you get much better results. So the correspondence autoencoder already gets really good results. Once you move to DCCA, so the deep canonical correlation analysis, you can see that even though it's unsupervised, so all of these here, they are supervised. This guy here is unsupervised, but still it manages to outperform some of these supervised ones. So like I said, it's still quite effective. And then, well, you have one classifier-based approach here, which performs fairly well. And then you have our final model, which basically combines the triplet loss with its adaptive formulation, where it actually outperforms all of the previous approaches. So I hope this gives you a good overview of the state of things in terms of performance in this kind of embedding models. So once we have this, I think we can start looking at some of the applications and some of the state-of-the-art the things that are done in the state-of-the-art and that are supported by this kind of models. So the first thing we can do is revisit the visual common sense reasoning approach. So like I said, we had a question, we wanted to answer a question about an image and provide an answer. So the architecture has these 3 main components, okay? It has a lot of things, but it's important to realize just the building blocks and find the patterns and connect to the things that I've shown you before. So we have this first block here. So it's a block that is learning a multimodal embedding. And then we have a contextualization block, which basically tries to compute some attention between the images and the text. And then we have a reasoning part. Well, if you want more details, you can see this, the paper. You have the reference here. But the important thing here is that all of these is possible because they managed to come up with a quite effective way to model the image, the objects that are in the image, and then the query that the question that someone asks, and then the possible responses, and merge everything in order to be very effective at unifying the modalities and answer the questions that require this unification. So it's one way in which these multimodal embeddings can be exploited, and you've seen that it's quite interesting. At least for me, I think it's quite remarkable. Another thing which you can do is bring extra information to these models. So I did this work last year, which basically the goal was to bring the time dimension to these embedding approaches. And the idea was that we wanted to model the evolution of vision and language. So we wanted to have a multimodal embedding, but we know that things change over time, so we want to capture things changing. So basically we have this data timeline and we want to preserve it. This was the goal, and we accomplished this. Basically, if you look at the architecture, so you can still see the same pattern of the 2 branches. So you have one branch for the images, one for the text. But now we have this third layer, which basically will be used to condition on intermediate representations of each of the other projection functions. And it will allow the embeddings to shift on time, based on time information. So everything is then jointly trained. And again, we used one of the components was triplet loss, and then we also had a second term, which was basically responsible for adding a set of rules to preserve data original timeline. If you want to really understand how this was, how the loss then is formalized, you can check the paper. The reference is here. So once we have this, we have a model that we can model vision, language, and time. So we got this data set, which has about 20 years of information, and we can do really cool things. So one of the things which we did was we took these two images from two tsunamis, and we measured the similarity over time. Okay, so -1 is minimal similarity, 1 is maximal similarity. And on the x-axis, you have the different instants in time. So the first point is that we take this image and we evaluate how similar it is to the rest of the data set over time. And we see that the peak of similarity, it's actually corresponding to the timestamps of these images. So this shows us one thing. We managed to preserve the data timeline, but it's also showing the evolution of these kind of things, because you know that in Japan, the tsunami was around 2011, 2012. It has nothing to do with the one in Indonesia. So even though they have the same category, we can still see these different patterns of evolution between the two things. So you could use this for any other two modalities that you can think about. The model would work the same way. The second thing we can do with this kind of model is basically we can automatically generate summaries just by following the temporal trajectories. So to give you an illustration, so we started with this image. So this is an image from the tsunami in Sri Lanka. So it was in January 2005. So if we go to the past, just 1 month before, we have an image of flooding in Indonesia. And if you do the same exercise, but now to the future, you find a text that is mentioned people talking about recovery and talking about the devastation, etc. If you go further to the future, so now 1 year after, there wasn't any tsunami in Sri Lanka, fortunately. So the most related thing, the most closest thing is were the floods in New Orleans. So basically the model kind of captured the semantic similarity between these two things over time. So you can do this. You can start with an image and find the text like I've shown you here, or you could do the opposite thing and the model would work the same way. And this is completely automatic. If you want to see more examples, you can check the paper. We have some more there. And finally, I want to just give you talk about this last model. So this was something that is very recent. It was published in 2009, and then it was the last version was the best performing version was published in CVPR this year. So it's quite recent, and basically it shows exactly where we are at these kind of approaches. So basically, it combines images and text, information from images and text using BERT. I'm sure that many of you know BERT. Basically, they took the transformer architecture, and if you notice that we have the same pattern. So we have one branch for the images and one branch for the texts. They found a clever way to transfer information between the two, and then they trained this on 12 data sets on 4 different tasks. And they really managed to outperform all of the previous state-of-the-art in several tasks, in visual question answering, in text grounding in the image. So where is this text expressed or this word expressed in the image, in multimodal verification, caption-based image retrieval. Well, it's a single model that outperforms all of the other specific models for each task, which is quite remarkable. And the main message, and I think the main research direction for this kind of approaches and this kind of embeddings is that multitask learning, a combination of multitask learning, so training on several tasks and then training it with several data sets, it's actually, well, the way that these things are taking and the direction that these things are taking. So to summarize and to give you a quick takeaway is that we can use these multimodal and cross-modal embeddings to effectively combine information from multimodalities. So I've shown you some of the basic building blocks. I did not have time to go into details on different types of architecture, etc. But I think it covers the fundamentals and some of the basic building blocks that you can find in more complex architectures. And then you can use these kind of things to feed your machine learning models and to use these representations and tackle other tasks that can leverage from combining the information from different views of your data. So I have here some pointers. You will have these slides available. They will be on GitHub. So you have all of these pointers if you are interested in reading more about the subject and, well, exploring for yourself these kind of techniques. So feel free to follow this information. And thanks a lot for listening. And I'll be happy to answer your questions.
Yeah, so let's give a quick thanks to David for this interesting talk, and it was very deep into the topic, and it was very cool to hear from you. So yeah, we'll start the Q&A session. We have a couple questions here on this chat, so we'll present them now. So I'll present the first one. Here it is. How do we deal with different frequencies in the modality? So if we have a modality that has a more frequency than another, how can we deal with this problem?
Okay, well, that's a great question. So it's basically all if you have this kind of imbalance in terms of modalities, so you inherit all of the problems from imbalanced datasets. So I guess that the way to go is just trying to use all of these techniques that you have for imbalanced datasets, like you can have sampling the class, well, in this case, the modality that which has less samples, do kind of data augmentation based on to assure that you can achieve a balanced representation. Then and all the other techniques that you have to deal with class imbalance, like weighting, etc. But these would be just, I would say, standard things. So if you are willing to really do a better job of doing these kind of things, I think you can exploit triplet loss to do this in metric learning. I don't know if they can see my slides. They can still see my slides?
We'll quickly show them, I guess.
So if you look at this, okay. So if you look at this expression, basically you are free to choose your anchor, your positive, your negative. So if you know that one of your class or your modality, let's say that it's text, you have very few texts, so you can control the generation of these triplets to make sure that it is balanced. And you can do your data augmentation directly here, and I think it's one way to approach it. But again, like I said, all of the approaches that you can use for dealing with imbalanced data sets, you can use this to train your model, because the problem is also always having a good embedding space that is not overfitted, in the sense that it is not just focused on the modality that is most represented.
Mm-hmm. Okay,
yeah.
Thanks for the answer.
I will make the second question. Hi, David.
Hello.
Can you give different weights to the modalities? Can you make weights?
Yes, sure. So I don't have that reference here. So one thing which I didn't talked about is that at some point on the network you need to combine it. Let me just put the network here. I think it's simpler to think about it if you look at an image. So here at some point you see that you have these two modalities. At some point you need to combine them in this kind of model, for example. So you can perform your weighting here, in the sense that you can just try to when you combine, there's different ways of combining. Concatenation wouldn't allow you to actually kind of introduce some weights, but if you multiply them, you can actually try to find a linear combination that minimizes the one that you want to minimize. So basically you would give a smaller weight. There's this work which in the RIPS, which is something like learning to combine multiple modalities, something like this. They go really into detail about that specific question. It's about the multiplicative idea. So basically combining them are multiplying, and you can exploit that product, that multiplication, to enforce your weights. So yeah, you can do that.
In your work, did you see that the image or the text was more important in the model?
Well, it depends on the data set and depends on the kind of images and texts that you have. For example, in the case of the tsunamis, the text is really good at discriminating because usually you have the location. So you have the place where it happened, or you can have also the name of the event. So it was a tsunami, it was a flood, etc. And these kind of things, visually, they may be very similar. Because a flood and a tsunami, if you think about it, if you have an image of the tsunami, but after the wave, so it's very similar to flood. So in that scenario, the image there would be some confusion in the image modality, but that text will help discriminate. And then you have the opposite. For example, you can have, we can be talk about colors, so the text won't help. So if you have like a blue flower and a red flower, so the text does not actually discriminate, but if you look at the images, it can really discriminate them. So the visual part is actually more important, for example, to detect different type of species of plants, for example.
Yeah, I actually had a question that just came up about this. Is there a particular combination of modalities that is harder to work with than others? For example, is combining audio and text harder than combining video and text or something like this?
The answer, I think, it's yes, because it's in the nature of how you represent those modalities. Because for images and text, so for still images, you have a single vector, right? For videos, there are strategies to come up with a single vector to represent your video, but you are compressing too much information on a single vector. So I don't know if it will work. So to get really the best performance, and especially in a video that can have multiple different things in it, you would need different vectors. So now you need to deal with multiple vectors, one modality that for each sample has multiple vectors. And so video would be harder. I think for audio, there's these fingerprinting techniques where you can still get a very good vector representation for specific segments. But again, you will also have these problems of segmenting the audio. Or because if you treat the audio as a whole, especially in speech, I don't think it's a good idea. So I think the difficulty comes from encoding, having a first good representation of these modalities, and then the rest of the models, you can use all of these. It will work the same way. Okay.
Yeah. So we have another question, which is somewhat what you talked about here. So how can we deal with ambiguity in the modalities? If one modality speaks one thing and the other modality says the opposite, right?
One modality says the opposite. Okay, so there's two things we have to realize. So the first thing is that these models, they are trying to learn a pattern between the interactions of the images and, one modality and the other. And if that would be an outlier, I think the model would just end up ignoring because it wouldn't find a pattern. So in other words, it would just ignore it, and that example would just work as noise to the model. If you really have this kind of data where the two modalities are kind of contradictory, but you find a pattern in that contradiction, so if it's consistently contradictory, then it's a pattern, then you can put them together in your multimodal embedding space. What I was thinking about is that there's a situation where, I don't know if this is also part of the question, which is if you have an image, the same image on two pairs, but with different texts, and the texts are really completely different, then that is a real problem. Because like I've shown you here, let me just quickly go through the same slide where we have the network. And what happens is that you give an image and the text as input, and this is everything the model has. It does not add anything else. Well, it can have supervised information, but let's say that you have this same image and two different texts, okay? And the texts are really contradictory. So let's imagine that instead of Pakistan, it was in Japan. And this is a problem, and it's actually one of the drawbacks not a drawbacks, but a limitation of these kind of net architectures. But if this limitation can be solved by the time dimension, then you can use these diachronic embedding models, because now you are what you are doing is that you are placing things over time. So if the temporal dimension solves your ambiguity, then you can exploit this kind of architecture instead, and it will be able to separate these two things. But the other models have that limitation.
Okay, thanks.
The following question is, can the model also combine sound and video?
Yeah, so
I think
I think I already talked about a little bit about that. The answer is yes. So basically, you can combine any modalities that you want. The only requirement to use all of the things that I've mentioned here is that you need to find one way to represent images or text, in your case, sound or video. So if you have a way to represent this in a vector, and that vector has some meaning, for example, it captures the things that happen in the video, then you can use everything that I've presented to you as is. It wouldn't give you the best performance for video like I was talking about. There are a lot of works that work with video, combining video information with speech information, because, well, the video has audio, so it's an additional modality. So a lot of works combine these two things, and they do this in more clever ways, because, like I said, in different parts of the video, you are talking about different things, and you are showing different things. So it's good that you look at different parts of the video and of your audio to get the best performance. But you can use all of these approaches as well.
Can not a video be decomposed as your temporal dimension? Is a sequence of image?
Yes, it is, but it's different. So let me try to. That's a good question. That's a really good question, because it's one of the differences between these diachronic embeddings. So here we are talking about time in an absolute manner. So basically, this is it's 20 years of information. Your video, the time scale or the time dimension of the video is completely different. It's just capturing a specific moment that would fall, for example, in March 2005. So you could have a video here, 10 seconds of a video in March 2005, which is completely different from what happened in January 2005. So what you are saying is that, yes, you have a sequence, but I think you could use these sequence-based models like recurrent neural networks for that kind of situation, for modeling the things that are in the video, unless your video is actually covering things from different moments in time. Well, that's another problem. So you would need to split your video based on those specific segments that refer to different points in time. And again, you could still use the sequence models to encode these segments and put them in this more global time dimension. I don't know if I was clear enough.
Makes perfect sense, yes.
Okay.
A large variation of information and not a small set of seconds in a video. Thank you.
Yeah, it also depends on your granularity, because here I'm showing, well, this is just an illustration, but if your time scale was in seconds, then that would make sense. If you take a frame for each, or if your video is a sequence, and if you take a frame for each second, and then if you can frame every part of your video in a specific timestamp, then you just need the starting point, then you would be able to use this diachronic cross-modal embedding. Yeah, but it's a very particular case.
Okay, so the next question is, can these kinds of models be used for agent planning, so robot actions, for example?
Okay, yes, the answer is yes. This is not my field of expertise, so navigation in robots and also in agent planning. But in any situation where you need to combine information from multiple sensors, so a camera is also a sensor. So you have cameras, you have proximity sensors, you know the map of, well, your the place where you want to navigate. So these are all different types of information, and to make the best decision, you need to combine all of them. So yes, you can use this to explore this kind of approach where you can, again, this is all based in patterns. So if you are if you can unveil a pattern that combines that tells you, let's say that for a specific part of your trajectory, some set of sensors are more important than the others, then you can combine the information of those sensors based on the patterns, of course, and then you can make a better decision. So yeah, you can use these kind of things. Also, actually, I have one of the in this motivation slide. This work here, which I have in the bottom, is actually doing some kind of this approach. So it's basically combining different types of information and making a decision based on all of this joint information.
The following question is: in other words, multimodal models are internal multi-target stacking.
Multi-target stacking. I don't know exactly what it means. What does multi-target stacking means? What is the multi-target here? Can the person that made the question clarify this, please?
So maybe we'll change to another question while the audience clarifies what stacking is.
Okay, thank you.
The other one is one of the sources unreliable, such as video feed, how to deal with the noise? I think the example that you write in the chat was, imagine different light sources, or if your light is pointed to the camera, something like that. How can the model deal with the noise?
So you would need something else, but yes, you can use this as a backbone, as a building block, but you would need something else, because what you're saying is that there are some parts of your, in this case, video that are noise. So you don't actually want to look at those parts when you combine information. So there are a lot of ways to remove noise from video. I don't know what kind of noise is, but basically one of the things which you can do is just kind of add an attention component over these things, and then when you're training the model, if you have these different, like I said, you have to have different segments encoded. So if you have a vector for each of your possible segments, then you can add an attention layer over each of these segments, and the model can learn which segments are more relevant and what types of segments are not important, and those can be the noise, which eventually will be the ones that do not help discriminate the patterns that you want to unveil. So yeah, you cannot do them just like they are here, but you can do it with some minimal changes.
Okay, thank you. We still don't have the definition for multi-tracking.
I think we have actually. So I'm quoting Konstantin, which was the person who made the question here. So he said, all stacking, sorry for calling it stacking, the approach is the same way in my view. Models suffer from overfitting. Cross-validation and stability is one of the main questions here.
Okay. I think I got the question now.
So his question is, did you face instability issues, basically?
Yes. Well, the short answer is yes. Let me try to give you some more details about this, because, well, like I said, it's important to just tell you the context in which I found those issues. So when you have these deep networks, well, you have all the problems of training deep networks. You need to deal with them. So it's important to use regularization. It's important to be careful at normalizing your features. Batch normalization also helps. So all of these strategies that you can use, gradient clipping also helps in some situations. So all of these things, it's important to use them, and you also need to be careful with the activation functions. And I think the best thing to think about now is how the state of the art is doing, and this is exactly the example that I've shown you about using BERT. So the transformer architecture, since it has those residual connections actually help a lot dealing with gradient vanishing and gradient exploding. So they were able to, that's why in BERT you can stack a lot of those transformer components, and it still works quite well. So I would check those type of architecture if you're really facing those issues, and I hope that I got your question right.
We have a follow-up regarding the multi-stacking target. I will read it. Let's say we have a tabular data with images. We can construct two different models, one for the tabular classification, one for the image extraction, and then we feed these models into a third model. So this is what it means by multi-stacking. Is your model similar to this one? Like you have different models that you combine and you stack different models, or the
yes, of course. I think we are just using different terminology, but yes. So the thing is, when I mention here the problems of the, so let me just go to the slide. This slide, when I mentioned here, is that when I talked about a single model, it's exactly that. So basically, a single model is not good for every kind of modality. So usually what we do is we have one model for text. For example, if you want to be really good at encoding a sentence, you would need to have a recurrent neural network, like, for example, I don't know, like an LSTM, or more recently you can use, now you have the BERT, which performs much better. So you can use BERT for text, and this is one model. Then you can use CNNs pre-trained on different data sets, which already gives you like a good structure or initial structure for your feature representation. In this case, in my work, I use a lot CNN trained on ImageNet, which is it's a set of 1,000 concepts, and the vector representations are quite good. So, like I said, it's completely different from text. And then you have a final model where you combine the two things, and this final model just is responsible for, like I said, combining the two things. And so it's three models in this case. So yeah, you stack models.
Yeah.
Okay.
He's happy with your answer. Thank you.
Okay.
Yeah, okay. So we're reaching actually the last two questions that we have here. So if you have further questions, make sure to write them down, and we'll display it to our speaker. I'll read the next one. So how can we deal with variable amounts of modalities? For example, fixed amount of text, but a variable amount of images, or the inverse?
I think this is related to the first question about the imbalance in terms of the frequency.
Yeah.
Well, like I said, ideally you don't want to overfit, in the sense that you don't want to just build your embedding based on the image part or one of the modalities. So ideally, you would have to find a way to make it balance, at least in the first training stage. So like I said, you can use the triplet loss, and when you choose the triplets, you can be very careful at choosing triplets such that you achieve a balance in terms of image and, well, modality, one of two modalities, like let's say modality 1 and modality 2 pairs. And this could be a first training stage. If you really have like lots of images and very few texts, what you can do, you can do some kind of pre-training and based on the image part, and then try to learn over that. It's important to realize that you always need to have paired data, or at least you need to be sure that the text is correlated with the image to train these kind of approaches. So in the end, you need to do some kind of sampling to ensure that you find a way that balances the number of examples that the model sees when it's computing the updates. So like you can use all of the techniques for imbalanced data sets. In practice, I think that's how you can think about it.
So I think this is the final question, at least until someone makes another one. Why should we use triplet ranking loss that requires negative examples instead of using cosine similarity loss or mean square loss that do not need negative examples?
Yes, that's a good question too. So, like I said, there's this field of learning the embedding space structure directly. So it's metric learning. And when you don't have the negative, you can only say that these two things should be similar, right? So these two guys should be, if you don't have the negatives, you just have, say, the positives. you can measure this cosine similarity, and you don't have this information about these two guys should be together and these other guys should be far apart. So this is a notion of the triplet in metric learning, and it's one way to approach it. You can actually train a model for a regression, or like I said, a classifier, where you just force it to, well, use Euclidean distance, for example, L2 loss, and to rebuild the representations or to approximate the representations. But you cannot only minimize, so you can, but there's a lot of work about this. And there's this conclusion where you can just look at the positive pairs, but if you also add negative pairs, so information from things that should be far apart, you can perform much better. And there's even extensions to these, to quadruplets and even more. So basically, well, you can imagine that people have been working on this field. So there's a lot of things here. But the main point here is that you can do it like that, like you said. But in metric learning, it really works well to better, at least it works fairly better to have this negative notion. So a notion of, I know that these two things should be together, and I have this third element that should be far apart. Okay, and it helps understanding how you should structure the space.
Yeah, so this actually resembles, for example, the silhouette score for clusters, right? Where we have the score for how similar a cluster is and how far apart it is from the others, right?
Yeah. Yes, exactly.
Yeah. Okay, so I don't know if we have any further questions. Doesn't seem like we do. So if there isn't any further questions, I'll again thank you, David, for taking the time to being here with us and talking about this subject. And yeah, hope to see you soon. And yeah, thanks for being here.
It was a pleasure. Thank you.
It was our pleasure.
All right. So again, guys, I just wanted to ask for your talks one more time. One example of this was actually David. David actually proposed his talk in our call for proposals. So if you have a talk that you find that is interesting and you want to share with the community, again, please feel free to fill in your information here in our call for proposals, and we'd love to give you a stage as well so you can share this message. And we also like to invite you to fill in our survey that we have. So it's basic feedback to how the webinar went, what you thought was good points and what you thought didn't work so well, so we can improve and give you guys even better meetups and webinars and yeah, improve in the future. So that is it from our meetup today. I hope to see you soon. In this case, it will be in the next webinar at August the 6th. And yeah, see you there, and take care, guys.
See you. Thank you for coming.